Welcome back to the Deep Dive. Our mission is to take a stack of dense sources, pull out the most important insights, and give you the knowledge you need fast. Today, we're deep diving into a foundational concept that underlies, well, almost all data processing, the string.
It sounds so simple, doesn't it? Just text. But for anyone learning to manipulate data, mastering the string is, it's non-negotiable. We're moving far beyond just defining text. We're really dissecting the properties, the hidden methods, and the crucial constraints that turn a sequence of letters into a powerful analytic object.
Okay, let's unpack this, because if you're coming into data science from a purely mathematical background, this is a huge paradigm shift. What's the foundational difference between numerical data, an integer, or a float and text data, these strings? Why does the computer treat them so differently?
The key difference is structure. A string
Yeah.
is fundamentally a compound data type. Unlike a single number, which is just one value in memory, a string is more like a container, a sequence of individual characters all stitched together.
So because it's a container, you essentially get two ways to interact with it.
Precisely. You get that duality. You can treat the whole thing as a single entity, like a name or a paragraph. Or, and this is the important part, you can traverse it. You can break it down, go character by character, and inspect every single element. That sequential nature is where the power is.
And that's where the concept of strings as objects becomes so valuable. Our sources really hammered this point home. The moment you define a string, you're not just holding text, you're holding a complete software object. And it comes pre-equipped.
It does. It's like buying an appliance that already has 40 functions built in. You don't have to code the basics yourself. They're just methods attached to the object. And for any learner who wants to see the full arsenal, you can just type help Mistral in your environment. You'll get pages of these built-in tools.
That's a fantastic shortcut. So looking at that long list, what are the high-value methods, the ones that instantly turn messy text into something useful? What's the essential toolkit?
The essentials definitely start with standardization. Text data is messy, so you need consistency. That means methods like upper and lower, absolutely indispensable for normalizing text before you compare or store it. You also have swap case and capitalize for more niche uses.
And what about, beyond just cleaning, how do you actually find stuff inside that object?
Right, for inspection, you've got powerful methods like enswith or isdigit, which let you quickly validate what you're looking at. But the methods that really unlock analysis are for extraction. Things like find, to locate a substring's position, count, to tally how many times something appears, and maybe the most powerful of all, split.
Oh, a split is a game changer.
It really is. You just give it a delimiter, like a comma or a space, and it instantly turns a long string into a workable list of smaller strings. That's step one for almost all NLP.
So strings have these built-in methods, but they also interact with the old arithmetic symbols, plus and multiply, but with completely different meanings.
That's one of the first things that trips up a new programmer, for sure. The plus operator, plus A, isn't addition, it's concatenation. It just welds two strings together. So hello plus world becomes hello world. And the multiplication operator, right, that's for repetition. You take the string run and multiply it by 5, you get run, 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 run.
Which is surprisingly useful.
Yeah.
Now, let's go back to that sequential nature. Since strings are sequences, we can pull out specific parts. Slicing, how does that work?
Slicing is essential. The basic bracket operator index just grabs one character, but the advanced slicing notation, that's where the precision comes in. Inglestart index, exclend index, SNEPA. You define your start, your stop, and remember the stop index is always excluded.
Right.
And the step lets you jump over characters, maybe grabbing every second or third one.
And I always find the negative indices super intuitive.
It is elegant, isn't it?
Yeah.
Using something like -1 lets you access characters from the end of the string, so you can grab the last character without ever needing to know the string's total length, which of course you can always get with the len function.
Okay, so we've seen how versatile they are, but our sources highlight a major guardrail, a fundamental law, the constraint of immutability. If they're so powerful, why can't we just edit them directly?
This is the moment where the deep dive truly begins, because immutability is the most crucial characteristic. And it's a design choice, not an accident. Once a string object is created in memory, its content cannot be modified in place.
Wait, I want to be absolutely clear for the listener here. If I have a variable with the word data, and I want to change the D to an L to make it LADA, I can't just go to index 0 and overwrite it.
You cannot. If you try that, the system will throw an error. Or, more likely, it'll create an entirely new string object, letta, in a different memory location. And then your variable just gets reassigned to point to that new string.
Wow.
The original data object is left untouched.
But doesn't that sound incredibly inefficient? If every tiny change creates a whole new string, isn't that just chewing up memory?
That's a great question. And it speaks to the trade-offs in language design. While it might seem inefficient for heavy edits, immutability gives you huge benefits. Crucially, it makes strings thread-safe and predictable. Since two parts of a program can't change it at the same time, you eliminate whole classes of bugs. It's a powerful guarantee of consistency.
Ah, so it's a foundational safety feature. That makes sense. Okay, so since we can't change them, one of the most common tasks has to be string traversal, just moving through the whole thing to analyze it.
Traversal is fundamental. And because they're sequential, it's simple. We usually use for loops, which are cleaner for simple iteration. But you can use a while loop if you need to manually manage the index for some reason.
And when we traverse, we often need to compare. How does a computer decide if apple is greater than banana? Especially with mixed cases.
The comparison is done lexicographically. And this is where the computer's character map, the ASCII values, they just take over. It's crucial to realize this isn't alphabetical order as we think of it. It's the numerical order of the character map. Every character, letters, spaces, punctuation has a number.
So the comparison is purely numerical based on those hidden values.
Exactly. The system compares character by character. The moment it finds a difference in the ASCII value, it stops. Whichever string has the higher ASCII value at that point is greater. This is why case matters so much. A capital Z has a totally different and lower ASCII value than a lowercase z.
Wait, I need to pause on that. You're saying if I compare zebra with a lowercase z to zebra with a capital Z, the lowercase one is actually greater numerically.
That's precisely right. In ASCII, all the uppercase letters come before the lowercase one, so they have lower numerical values. Zebra is greater than zebra. It's a classic pitfall when you're sorting data. If you ever need to check this, the function ordz will show you the exact ASCII value for any character.
That tool alone will save people hours of confusion. Now, is there a simple way to test if one string is inside another without writing a whole loop?
Absolutely. That's substring membership. We just use the in and not in operators. It's super convenient for quickly filtering or validating data.
And speaking of validation, one of the most common real-world tasks is just data cleanup. Getting rid of stray spaces, punctuation, all that junk.
Which loops right back to immutability and traversal. The way you clean a string is you traverse the original, inspect each character, and then build a brand new clean string, leaving out the stuff you don't want.
Let's pivot to presentation. Once you've done all this work, you need to display the results in a readable way. This is where string formatting becomes essential.
Formatting is all about making output look good and predictable. The format method is the most powerful tool for this. The core of it is using curly braces as placeholders.
And you can put numbers inside those curly braces to organize things, can't you?
Yes, the numbers are optional but really helpful. They let you reference the arguments you pass to the method by their position argument 0, 1, 2. It lets you reuse variables or change the display order easily.
But the real deep dive detail is that those braces can contain format specifications that control alignment and even data types.
Well, this is where you elevate your output from a jumble of text to a structured table. Alignment is a huge part of it. A caret for center, less than for left, and greater than for right.
Can you give us a specific, audible example of that power?
Sure. Imagine you're printing a receipt. You want the item name left aligned and the price right aligned. You might use a spec like 1.5 for the item name, that's left align argument 0 in a 15-character space, and 1.15 for the price. It forces your output into these neat columns.
And it handles data type conversion too, which is critical.
Absolutely. You can use F for floating point numbers. So 0.2F makes sure a number always has 2 decimal places, perfect for currency. Or on the more technical side, X will convert an integer right into its hexadecimal form inside the string. It's incredibly versatile.
So if we connect all these pieces, immutability, slicing, comparison, formatting, they aren't just academic. They let us solve real algorithmic puzzles.
They absolutely do. Mastering these basics is the foundation. Take the classic palindrome check, determining if a string reads the same backward as forward, like madam.
Right. Seems simple enough. But how does that connect to efficiency?
Well, the brute force way is to reverse the whole string and then compare it to the original. But the efficient way uses traversal with two pointers. One starts at the beginning, one at the end, and they move inward, comparing characters. The moment you find a mismatch, you stop. It's much faster and uses less memory.
So that's a great example. Another key application from our sources was run length encoding, or RLE.
RLE. A brilliant, practical application of all these concepts. It's a form of lossless data compression, where you store a sequence of identical characters, a run as a single value and a count.
Okay, so walk us through the example. How does ABC get compressed?
To compress ABC, you have to traverse it. You start at A, you count that it runs for 4 characters. So you append 4A to your new compressed string. Then you move to B, that's a run of 2. You append 2B. Finally, C is a run of 1, so you append 1C. The result is the new immutable string, 4A2B1C.
And decompression uses the skills we just talked about. To get 1E2B3C back to the original, you'd have to traverse it and use that repetition operator.
It's the perfect loop. You read the number, read the character, then use the operator to generate that many characters. So 1A becomes A, 2B becomes B, and 3C becomes CCC. It just proves that even advanced things like data compression are built on basic string traversal, counting, and operators.
We started this deep dive talking about simple text, and we've ended up with these powerful, immutable objects capable of complex formatting and data compression.
Exactly. So you now understand that when you see text data, you're not just dealing with letters. You're dealing with a whole toolkit, all governed by that strict rule of immutability and the speed of ASCII comparison. And that raises an important question. The source has established that the RLE process requires generating a brand new compressed string because of immutability. Consider how that and the character-by-character comparison aren't just features, they are essential guarantees. They ensure you can reliably decode and recover the original sequence perfectly every single time. So what other common tasks that rely on absolute accuracy, like, say, spell-checking algorithms or data validation in a web form, are fundamentally built on these same basic string operations and their underlying ASCII values? Something to mull over until next time.